Hey, hello everyone. So in this movie clip, I'm going to begin the great details on drift in chapter 3. So as I described before, the mechanism of drift is very associated with a voltage difference or electric field. So in this figure, you can see that there exists a voltage difference because of this battery voltage source. Okay, so from plus electrode toward the minus electrode, the electric field is formed, and within this region, a negatively charged particle, which is electron, has been it is existing. Then, uh, the electron would receive a certain amount of force coming from the electric field. So based on the basics of electromagnetics, the field to be applied to this single free electron is proportional to the intensity of the electric field applied onto the electron. And this force is proportional to the electric field. And if we are talking about the one-dimensional space, so this electron is moving left side or right hand side. That's it. It cannot move up and down because the movement of kind of tra train rail, the electron is moving along the x direction only. So we can simplify the mathematics from vectors down to algebra. So force is proportional to the electric field, and the proportional coefficient is how much charge the single electron has. But I said a single electron, so it has a unit charge and it is negatively charged. So electric field intensity or field, if I'm saying that the uh, positive value of electric field indicates, positive value means from left to right hand side, which is matched to the plus x direction. Okay, and then the force applied onto the single electron uh, is negative has a negative value indicating the minus x direction the force is applied onto the single electron because it is negatively charged. So that's the reason why I use the minus sign to indicate the force direction, and electric field direction is quite opposite if negatively charged particle is existing with in this electric field region. Okay, so now F is equal to minus Q times electric field E. So E is quite similar to the another E, right? So this E indicates the electric field and this E indicates energy, okay? But in this PPT slide, it was hard to uh, note this type of E. So let me correct here, okay? Okay, so F is applied onto the single electron. Then following the second law of Newton's second law, F is equal to its mass times its acceleration. Okay, and what is the mass of the single electron? As we have learned, I have strongly recommended you to memorize all the values of important constants introduced in chapter 2. Okay, so one of them is free electrons mass. That was 9.1 times 10 to the minus 31 kilogram. So plug in this value here, okay? And once we know the voltage value and the length in between two electrodes, then we're gonna calculate the electric field intensity, right? The electric field intensity is voltage divided by the distance, okay? And since we know the unit charge value, that is, and 1.6 times 10 to the minus 19 coulomb. Okay, so plug in those values and you're gonna estimate the acceleration value. Okay. So now let's repeat this simple estimation in case of semiconductor instead of vacuum. So previously I said there is nothing. So we can claim that this single electron is existing in vacuum. But now the free electron is existing in semiconductor. Okay. Then on the left hand side, we're gonna apply a positive voltage. On the left hand side, we're gonna apply the negative voltage. And this voltage difference is, say 2V, because we applied plus V and minus V on the right hand side. The voltage difference is V minus V, so 2V voltage. So this battery has a 2V, so we're gonna have a 2V voltage. Then what is the force applied onto this single electron in semiconductor? Well, same, right? Once we know the electric field intensity for the electron in semiconductor, and we can simply estimate the force applied on the, the electron in semiconductor. F is proportional to the electric field density, and we can write down this equation as we have done for the Cume case. And on the right hand side, you can see a single difference. Acceleration A is same, but here m sub n asterisk asterisk. Okay. So this asterisk is a symbol to denote the effective mass. Okay. Instead of using a simple mass, once asterisk is included as a superscript for a symbol or a sign, then you may expect that this asterisk is indicating effective something. The sign that symbol that we have used is a small m, which indicates the mass. So asterisk m, wow, that is indicating an effective mass. Then herein the question is, what is effective mass compared against mass? The mass has been measured in vacuum without any interference, without any perturbation, without any obstacles. Okay, without anything, the mass itself should be measured. That is the mass that we are talking about in real life. However, you know your mass, your weight would be different where depending on where you are. If you measure your weight on Earth, compare against if you measure your weight on Mars or on Moon, then the mass would be very different. If you take a look at the scale, your scale bar, scale arrow is indicating different number depending on where you are. Why is that? The main reason is gravitational force is very different. Okay? So that kind of thing can be happened in the case of electrons in semiconductor. Electron in vacuum versus electron in semiconductor. That is the very first topic in chapter 3, drift apart. Okay, so to explain uh, how heavy or how light a electron in semiconductor is, we're gonna use effective mass instead of mass. Okay? So here Mn asterisk has been denoted. Now, carrier's effective mass can be determined in an electric field E. Okay, an electron or a hole can be accelerated because of this electric field, right? So the acceleration value A is equal to the minus Q times electric field intensity E divided by Mn asterisk. Similarly, you can estimate the acceleration value for holes. And on the bottom side, you can see a table summarizing how light or how portion of the effective mass for a given simple mass has been well summarized for each semiconductor material. So in silicon, the effective electron mass is about 26% of the real mass. And in case of hole, 39% of you know the mass is effective mass in silicon. And in germanium, in gallium arsenide, the effective mass of hole is quite different. So depending on where the free electrons and holes are moving around, its real effective mass can be determined. It's quite similar what you would like to do as your job. Depending on where you are pursuing your graduate degree, MS degree, PhD degree, it would slightly or significantly affect your future career goal. This type of concept would be helpful to understand, just you know, intuitively understand the effectiveness of electrons and holes. Okay, let me stop here. I will do my best to quite often stop, and please have a short break time. And I'm going to get back to the other movie clip. And the next topic is thermal velocity, which is the average electrokinetic energy in silicon material. So how to estimate how fast, how slow the free electrons and holes are moving in the crystalline silicon material. How to estimate it? What is the good measure? Please think about this issue. And I will get back to you soon. See you.